Hello everyone. So today's lesson is going to be regarding chapter 8, which is all about alkyl halides and elimination reactions. So in one of the previous lessons, you learned that there are three general types of organic chemical reactions. There's the substitution reaction, there's elimination reaction, and addition reaction. And in the previous lesson, you learned all about substitution reactions, that there are two different types. There's SN1 and SN2 reactions. And in this chapter, we're going to focus on elimination reaction. And just like nucleophilic substitution reaction, elimination reaction also has two types. There's E1 and E2. And then we're going to take a look at the different characteristics of elimination reactions, the products of elimination reactions, and the two different types or mechanisms of elimination reactions. So one of the most important features of elimination reactions is the cleavage of sigma bonds to form a pi bond. And so we're going to focus on elimination reactions primarily in alkyl halides. So alkyl halides undergo elimination reactions with Bronsted-Lowry bases. The elements of hydrogen halide are lost and an alkene is formed. So again, alkenes are compounds containing double bonds. And so you can see that in this one example of elimination reaction here of this alkyl halide, in which the sigma bonds of the carbon and the hydrogen, as well as the sigma bond between the carbon and the leaving group or the halogen, are cleaved. And so what you have is the formation of a pi bond, which is contained in a double bond. So this is the general pattern in elimination reactions. You have two elements that are removed from two adjacent carbon atoms, and then a double bond or a pi bond is formed between those two same adjacent carbon atoms. So one important difference between elimination reactions and nucleophilic substitution reactions is right over here. So it says alkyl halides undergo elimination reactions with Bronsted-Lowry bases. In substitution reactions, the alkyl halides will undergo substitution reactions with nucleophiles. And if you remember, nucleophiles are Lewis bases. And the definition of Lewis bases, or the definition of a Lewis base, is different from Bronsted-Lowry base, right? A Bronsted-Lowry base will attack a hydrogen. It will react with a hydrogen via a proton transfer reaction. A Bronsted-Lowry base will react with a Bronsted-Lowry acid. But with nucleophiles will react with electrophiles. And electrophiles are the electron deficient atoms, mostly carbon atoms. And so a nucleophile will attack anything that's electron deficient because they are electron pair donors. They will donate an electron pair to any electron deficient atoms. However, in elimination reactions, we're using Bronsted-Lowry bases, and Bronsted-Lowry base will attack only a proton, a hydrogen, not an electron deficient atom. So that's the main difference between elimination reactions and substitution reactions. So here are two examples of elimination reactions in which the base, the Bronsted-Lowry base, attacks a proton. It will deprotonate this hydrogen right here that's bonded to this carbon atom, and this results in formation of a double bond between the two adjacent atoms right here. And then the sigma bond between the bromine and this carbon atom will be cleaved, which makes bromine a leaving group. All right, so let me show you the movement of electrons here. So again, we'll have this base right here, this Bronsted-Lowry base that will deprotonate this hydrogen. And then the two electrons will move towards this carbon right here, which will then result in the formation of a double bond. And at the same time, the lone pair, the sigma bond between this carbon and this bromine, will break, and then the lone pair will be transferred towards the leaving group, which is the bromine atom. So what results is the formation of a pi bond between the two adjacent carbon atoms. And then of course you have your base here that turns into a conjugate acid, and then the leaving group, bromide ion. And here's another example here. You can see that we have a Bronsted-Lowry base, which then will attack this hydrogen right here and deprotonate this. Here's the movement of the electrons. and then the sigma bond will break between the hydrogen and the carbon atom. And then the lone pair of electrons that moved toward this carbon atom will form a double bond with the adjacent carbon atom bonded to this chlorine atom right here. So here's a double bond, and then at the same time, the sigma bond between the carbon and the chlorine will break, which makes chlorine the leaving group. And so what's formed is a pi bond between the two adjacent carbon atom. In elimination reactions, the process of removing a hydrogen halide is known as dehydrohalogenation. So it's the removal of a hydrogen and a halogen within a molecule. Hence they call this dehydrohalogenation. And dehydrohalogenation is an example of a beta elimination. And beta elimination is simply the removal of a hydrogen that's bonded to a beta carbon. So this carbon right here is known as a beta carbon. How do we know it's a beta carbon? Well, it's because it's bonded to an alpha carbon. So any carbon atoms bonded to an alpha carbon is considered a beta carbon. And so now the question is, how do we know which one is an alpha carbon? An alpha carbon is a carbon that's bonded directly to a leaving group, like a halogen right here. So if you have an X bonded to a carbon or any halogens bonded to a carbon, immediately that carbon is considered an alpha carbon. And any carbon atoms bonded to that alpha carbon are beta carbons. And so in a dehydrohalogenation process, a base, a Bronsted-Lowry base, will attack a hydrogen bonded to a beta carbon. And then the lone pair of electrons from this sigma bond here that's broken will turn into a double bond. And at the same time, the sigma bond between the alpha carbon and the halogen will break. And now you have a pi bond, a double bond. So here's a table that lists some of the most common bases used for dehydrohalogenation. The most common bases used in elimination reactions are negatively charged oxygen compounds, such as hydroxides and alkoxides. So you can see we have sodium hydroxide here. It contains negatively charged oxygens. You can use sodium hydroxide, potassium hydroxide. You can use alkoxides like methoxides, ethoxides, and tert-butoxides. So these are some of the most common bases used in dehydrohalogenations. So how do we draw the products of an elimination reaction? So the first thing that you want to do here is to find the alpha carbon. Okay, you want to find the carbon that's bonded directly to the leaving group, like the bromine atom. So in that case, our alpha carbon is this carbon right here that's bonded directly to bromine. And so any carbon atoms bonded to this alpha carbon are considered beta carbons. And these beta carbons, as you can see here, contain a bunch of hydrogen atoms. And so now that we've identified all the beta carbons with hydrogen atoms, remove the elements of hydrogen and the leaving group, which is the bromine atom, from the alpha and beta carbons, and then form a pi bond. Since these beta carbons here are equally similar, the hydrogen atoms bonded to them are also equally similar. So that means that the hydroxide ion, which is the Bronsted-Lowry base, can attack or deprotonate any of these hydrogen atoms bonded to the beta carbons. And so we could potentially have different products from this dehydrohalogenation or elimination reaction. So let's take a look. So if the Bronsted-Lowry base attacks or deprotonate one of these hydrogen atoms, then we could have a double bond that's formed between these two adjacent carbon atoms, breaking this sigma bond between the carbon and the bromine atom, which makes bromine the leaving group. And so a double bond here would be one of the potential products, or a double bond will form between these two carbon atoms if the hydroxide deprotonates one of these hydrogen atoms here. Or a double bond between these two carbon atoms if the hydroxide deprotonates one of the hydrogen atoms bonded to this beta carbon. So as you can see, these three structures here are actually one and the same. They're all identical structures. Okay, so these are all identical. So in that case, we only have one organic product that's generated from this elimination reaction. And then of course we also have the byproducts, which would be water in this case, because the hydroxide reacts with one of the hydrogens here. So we'll have water, plus the leaving group, which is the bromide ion. And here's another example here, but this time we now have two different types of beta carbons. You have this beta carbon right here, which contains 3 hydrogens, and then this beta carbon right here that contains 2 hydrogen atoms. And so again, here's our alpha carbon, which is bonded directly to the leaving group, which is the bromine atom. And so, and then we have this Bronsted-Lowry base right here. So it could attack either one of these hydrogens. And so let's say that this Bronsted-Lowry base attacks this hydrogen right here and deprotonates it, then we can have a double bond that's formed between this beta carbon and the alpha carbon. And of course, bromine is the leaving group. So we can go ahead and draw one of the possible alkene here. So this would be one possible product in which the double bond is between beta 1 and the alpha carbon. Or we could also have a double bond between this alpha carbon and the beta 2 carbon. So if the Bronsted-Lowry base deprotonates this hydrogen, then we have a double bond between these two adjacent carbon atoms. So now we can have a double bond between the alpha carbon and beta 2 carbon. And of course the byproducts, which would be an alcohol, a tertiary alcohol, and the bromide ion. So here's practice problem number 1. Label the alpha and beta carbons in each alkyl halide, and then draw all possible elimination products formed when each alkyl halide is treated with potassium terbutoxide. So for the first alkyl halide here, the very first step is to identify the alpha and the beta carbons. So an alpha carbon is the one that's bonded directly to the chlorine atom. And any carbon atoms bonded directly to the alpha carbon is considered a beta carbon. All right, and this beta carbon atom contains 2 hydrogen atoms. And so now the Bronsted-Lowry base, which is the terbutoxide here, will attack or deprotonate one of these hydrogen atoms. And so let's say that this base deprotonates this hydrogen atom, and then a double bond will form, or a pi bond will form between the beta carbon and the alpha carbon, and at the same time this sigma bond will break, and then the lone pair of electrons will be transferred to the chlorine atom, which is the leaving group. So now the only product here would be, or the only organic product is this one with the double bond, and then a byproduct would be the chloride ion and tert-butanol, a tertiary carbon atom, or a tertiary alcohol. And for the next alkyl halide here, we have this alpha carbon right here, and then we have several beta carbons. We have this beta carbon right here, this beta carbon right here, and another one right here. So you can see that these two beta carbons are actually similar. Okay, so we can call this beta 2 and beta 1. So that means that we're going to have, since we have two different beta carbons, we're going to have two different alkene molecules. All right, so we can have a double bond that's formed between beta 1 and alpha carbon, or one of these beta 2 carbons and the alpha carbon. So let's draw the first product here. So the first one would be a double bond here. Or a double bond between beta 1 and the alpha carbon. And of course the byproducts. And for the third alkyl halide here, we have 1, 2, 3 beta carbons. And 2 of them are also the same. So we will have beta 1, beta 2, and the alpha carbon right here. And so we could have a double bond between beta 1 and the alpha carbon, a double bond between the alpha carbon and the beta 2. So those are the two possible alkene molecules here for this specific chemical reaction. So the first product would be a double bond between alpha and beta 1, and the other possibility is beta 1 and beta 2. Alright, so those are the two possible alkene molecules plus the byproducts. So alkenes, as I mentioned earlier, are unsaturated hydrocarbons containing carbon-carbon double bond. So that means that they contain a pi bond and that both carbon atoms involved in the double bond are sp2 hybridized. And because they are sp2 hybridized, they have a trigonal planar geometry with 120 degree bond angles as shown here. So these adjacent carbon atoms that are involved in the double bond are sp2 hybridized with trigonal planar geometry and 120 degree bond angles. You learned in the first chapter that a double bond contains a sigma bond and a pi bond. A sigma bond is formed via the overlap between two sp2 hybrid orbitals, whereas a pi bond is the overlap between two unhybridized 2p orbitals that lie above and below the plane. And so this pi bond is formed during elimination reactions. So just like the other functional groups like alcohols, amines, amides, and alkyl halides, alkenes can also be classified based on the number of carbon atoms bonded to the double bond. So for example, if we have one carbon atom bonded to this double bond, then we have a mono-substituted alkene. If we have two carbon atoms bonded anywhere on this double bond, then we have a disubstituted alkene. We can have tri-substituted with 3 carbon atoms, or tetra-substituted with 4 carbon atoms. So this will become important later on when we start talking about stability of alkenes. Here's practice problem number 2. Classify each alkene in the following vitamins by the number of carbon substituents bonded to the double bond. So here we have vitamin A, and you can see that it contains a lot of double bonds. And so in order to classify the double bond, we have to look at the number of carbon atoms bonded to the double bond. So for the first one here, we have 1, 2, 3, and 4. So that means this is a tetra-substituted alkene. All right, and for the next double bond here, we have 1 and 2. So this one is di-substituted. And the third one right here contains 1, 2, 3 carbon substituents. So this is going to be a tri-substituted alkene. And then this part right here contains 1 and 2 carbon atoms. So again, this is a di-substituted alkene. And the last one contains 1, 2, and 3. So this one is also a tri-substituted alkene. And for the next one here, we have vitamin D3, which contains 1, 2, 3 alkene functional groups. So the first one right here, the bottom, is a di-substituted alkene because it contains two carbon atoms bonded to the double bond. And then for the second one here, we have 1, 2, 3 carbon atoms. And so we have a tri-substituted alkene here. And finally, this top one right here contains 1, 2, 3 as well. So it's going to be tri-substituted alkene. Remember that alkanes contain only single bonds. So that means that they can have several different conformations. The reason why is because of the nature of the sigma bonds. It allows the molecules to rotate around and can have many different conformations. You can have anti-conformation, eclipse conformation, you can have gauche conformation. So that's basically the nature of sigma bonds. And these two structures right here, we have butane in anti-conformation, and if you rotate this 180 degrees, then it can have an eclipse conformation. So they may have different conformations and different overall energies, but they actually represent the same exact molecule. It's still butane. But for alkenes, it's a different story, because now we're dealing with double bonds, and double bonds contain pi bonds. So this double bond basically restricts the molecule from rotating around, and so it can't have different conformations around that bond. And so the only way you can rotate the molecule is if you were to break that pi bond. And so because of that, because of its restriction in bond rotation, these two molecules right here are two completely different molecules with different properties. You have a cis molecule and then a trans molecule. And so again, they don't interconvert between the two stereoisomers, right? Cis and trans. And so because of that, again, they're two different molecules. And again, because alkenes have restriction on their bond rotation due to the presence of the pi bond, there are two stereoisomers possible for alkenes. You can have a cis isomer or a trans isomer. And cis and trans isomers are actually diastereomers because they are non-mirror image stereoisomers. So we have an example here. We have cis-2-butene and trans-2-butene. And a cis-butene has the two methyl groups on the same side of the double bond, whereas in trans-butene, you have the two methyl groups on opposite sides of the double bond. So here's a few requirements in order for an alkene to be considered cis-trans diastereomers. So here we have a double bond. We have an alkene with a double bond, and this double bond contains 1, 2, 3, 4 substituents. So there's a total of 4 substituents bonded to this double bond. And in order for an alkene to have cis and trans isomers, the X and X prime should be different. In addition, the Y and Y prime should also be different. On the other hand, X and Y here can be the same. They don't have to be different. Same goes for X prime and Y prime. The same is true for X and Y prime, and Y and X prime. So again, they don't have to be different. They can be similar. The only two exceptions here are the two substituents bonded to that same carbon on the left and right of that double bond. So here's practice problem number 3. For which double bonds are stereoisomers possible? So in order for stereoisomers to be possible, the X and X prime should be different, and the Y and Y prime should also be different. Basically, we're talking about the two substituents bonded to the carbon atoms involved in that double bond. So for the first one here, we have an alcohol. You can see that the X and X prime here are the same, and so not possible for the first one. And for the second one here, we have two double bonds, and so we have to check both double bonds here. So for the first one here on the left, we have the X and X prime, so two substituents bonded on the same carbon. The two substituents are similar, and so not possible for this double bond. But on this second double bond here, you can see that the X and X prime are different, and the Y and Y prime are also different. And so stereoisomers are possible for this double bond. And for the third one here, we have, again, two different double bonds. So you can see that the substituents are different, bonded to this carbon atom right here. The substituents that are bonded to this carbon atom are also different. And so this one is possible. On the second double bond here, you can see that this carbon is actually similar to this carbon because they share the same ring. And this is a cyclohexane ring, and so not possible for this one. And here's practice problem number 5. Label each pair of alkenes as constitutional isomers, stereoisomers, or identical molecules. In order for a pair of alkenes to be considered stereoisomers or identical molecules, you have to look at the position of the double bond. So if the double bond on one alkene is on the second and third carbon, then the double bond on the second alkene should also be in the same position on the second carbon and the third carbon. Otherwise, they're going to be constitutional isomers. So when you look at the first one here, you can see that the double bonds are in different positions for the alkenes. And so most likely these two are constitutional isomers and not stereoisomers or even identical molecules. And so for the first pair right here will be constitutional isomers. And for the second pair of alkenes here, you can see that this double bond is between the second carbon atom and the third carbon atom, counting from the left. And on the second alkene, the double bond is also on the second carbon atom and the third carbon atom, counting from the right. And so when you rotate this molecule here, this first alkene here on the left, it will look exactly like this molecule on the right. And so they are identical molecules. For the next pair of alkenes here, you can see that the position of the double bond is the same for both molecules. And the only difference here is the orientation of the substituents. You can see on the left-hand side here that these two substituents are on the same side of the double bond. Whereas on the second alkene here, you can see that the two substituents are on the opposite sides of the double bond. So you can see that one of them is cis and the other one is trans. And so therefore, part C here is a pair of stereoisomers. And for the last pair of alkenes here, you can clearly see that the placement of the double bond is different for both molecules. And so they can't be identical molecules and they can't be stereoisomers. So they must be constitutional isomers. And you can always double check the chemical formula and you'll see that they are the same, they have the same chemical formula, and so therefore they're considered constitutional isomers. In terms of the stability of alkenes, transalkenes are generally more stable compared to the cis isomer. And the reason why is because the substituents in the trans isomer are far away from each other as possible. Whereas in the cis configuration, or the cis isomer here, the two substituents are on the same side of the double bond. And so there's going to be some steric effects here, steric hindrance, which increases the overall energy of the cis isomer. And so the energy of the cis isomer is greater than the overall energy of a trans isomer. And so that makes the trans isomer more stable than the cis isomer. So I mentioned earlier in one of the previous slides that the stability of alkenes is dependent upon the number of R groups bonded to the double bond. So as the number of R groups or number of substituents bonded to the double bond increases, the stability of the alkene also increases. So you can see that tetrasubstituted alkenes are more stable than trisubstituted, and trisubstituted alkenes are more stable than disubstituted, and so on and so forth. So again, as the number of R groups bonded to the double bond increases, the stability of the alkene also increases. So you can see these three different alkenes here. We have 1-butene, which is monosubstituted. We have cis-2-butene, which is disubstituted, and trans-2-butene, which is also disubstituted. So you can see that the cis-2-butene is more stable than the 1-butene because of the fact that it's disubstituted versus monosubstituted. And between cis and trans, the trans-2-butene is more stable because the two substituents are on the opposite sides of the double bond. So the stability of alkenes can be attributed to the concept of hybridization. We know that the two carbon atoms involved in the double bond in alkenes are sp2 hybridized. So that means that they contain 33% S character. And we know that the higher the percent S character, the more readily an atom accepts electron density. And so the sp2 carbons are more able to accept electron density, whereas sp3 hybridized carbon atoms are more able to donate electron density. And so you can see here that the sp2 hybridized carbon atoms are able to accept electron density coming from the sp3 hybridized carbon atoms. And so increasing the number of electron donating R groups, which are the sp3 hybridized carbon atoms, makes the alkene more stable. So these sp3 hybridized carbon atoms are considered electron donating groups. They can donate electron density towards the sp2 hybridized carbon atoms a lot better compared to hydrogen atoms. And so if you were to increase the number of carbon atoms bonded to the sp2 hybridized carbon, then it makes the alkene a lot more stable. So here's practice problem number 6. Which alkene in each pair is more stable? So for the first pair of alkenes here, you can see that both alkenes are actually disubstituted because they contain two R groups bonded to the double bond. And so the only difference between them is in their stereochemistry. One is a cis isomer and the other one is a trans isomer. And so we know that trans isomers are more stable compared to cis isomers. So in that case, this one is more stable. And for the second pair here, you can see that we have a trisubstituted alkene and a disubstituted alkene. So let me write that down. So this one is a trisubstituted and this one is a disubstituted. So in that case, the trisubstituted one is more stable than the disubstituted alkene. And here's practice problem number 7. Rank the following alkenes in order of increasing stability. So remember that the more substituted an alkene is, the higher the stability. So let's classify these alkenes. So the first one here on the left, we have 1, 2, 3 R groups. So this one is a trisubstituted alkene. And then the second one here only has one R group bonded to the double bond. So this is a monosubstituted alkene. And then the third one here contains 1, 2 R groups. So this is disubstituted. And finally, this double bond right here contains 1, 2, 3, and 4. So we have a tetrasubstituted alkene. So in that case, D is the most stable. So D is the most stable, followed by A, and then C, and then finally B. So B is less stable than C, C is less stable than A, and A is less stable than C. So it increases from left to right, where D is the most stable. So just like the substitution reactions, elimination reactions also have two different mechanisms. We have the E2 and the E1, which is similar to the SN2 and the SN1 mechanism in nucleophilic substitution reactions. And they do have some similarities. So for example, an E2 mechanism is also bimolecular, similar to an SN2 mechanism. An E1 mechanism is unimolecular, which is also similar to an SN1 mechanism. The E2 and E1 mechanisms differ in the timing of bond cleavage and bond formation, but similar to the SN2 and SN1 mechanisms. E2 and SN2 reactions have some features in common, as do E1 SN1 reactions. So we'll take a look. So the first one here is the E2 mechanism, and E2 mechanism is the most common mechanism for dehydrohalogenation, and it has second order kinetics. So you can see this rate law equation here, that this is a second order reaction overall. And this reaction is concerted, meaning all the bond breaking and bond forming happen all at the same time in a single step. So there's no formation of a carbocation or a reactive intermediate in an E2 mechanism, which is actually similar to the SN2 reaction. So here's an example of an E2 reaction, and you can see that we have an alkyl halide here reacting with a strong base, which is a hydroxide ion. And you can see that this alkyl halide here is a tertiary alkyl halide because it contains, this carbon atom is connected to 1, 2, 3 carbon atoms. And so we have a tertiary carbon, which makes this a tertiary alkyl halide. So this carbon atom that's bonded directly to this halogen is the alpha carbon. And so this alpha carbon has 3 carbon atoms bonded to it. So these are the beta carbon atoms. And so that means that this strong hydroxide ion right here, strong base, can deprotonate any of these hydrogen atoms bonded to the carbon atoms. And so when this base deprotonates one of these hydrogen atoms, then a double bond will form between the two adjacent carbon atoms, resulting in the cleavage of the sigma bond between the alpha carbon and the bromine atom. And so what you have is the formation of a double bond, which is the alkene here. So this is the organic product. And then we have byproducts, the leaving group, and water. And again, this happens all at the same time. All the bond breaking and the bond forming, they all happen in a single step, which makes this reaction a concerted reaction similar to an SN2 mechanism. And the only difference between the E2 and the SN2 mechanism is the classification of the alkyl halide. So remember that in SN2 reactions, we would want to use a primary alkyl halide or a methyl halide, not a tertiary alkyl halide. So here's the summary of the E2 mechanism. Again, we have an alkyl halide here that's reacting with a strong base, and the carbon that's bonded directly to the halogen is considered the alpha carbon, and any carbon atoms bonded to the alpha carbon will be considered beta carbons. So 1, 2, and 3, these are all beta carbons. So the hydrogens that are bonded to these beta carbon atoms could react with the strong base, and so this hydroxide ion can deprotonate any of these hydrogen atoms or the hydrogen atoms bonded to these other beta carbon atoms. And so when one of these hydrogen atoms gets deprotonated, then you can have a double bond that's formed. And at the same time, the sigma bond between the alpha carbon and the bromine atom will be cleaved. And so now you have a leaving group, which is the bromide ion. And you have the organic product, which is the alkene. And water is also one of the byproducts. So again, this happens all in one step, and they call this a concerted reaction. And as I mentioned earlier, there's a lot of similarities between the E2 and SN2 mechanisms in how the identity of the base, the leaving group, and the solvent affect the rate of reaction. And here's the energy diagram for an E2 reaction. You can see that there's only one hump here, one activation energy, one transition state for an E2 reaction, because it doesn't have a reactive intermediate. So there's no rate determining step, so it only involves one single step, which makes this reaction a concerted reaction. So as you can see, the energy diagram is sort of similar to an SN2 reaction. The only difference here is that the transition state is different. So you can see here that there's a total of 1, 2, 3, 4 partial bonds that formed in the transition state of an E2 reaction. In an SN2 reaction, there's only 2 partial bonds. The partial bond that's being formed between the nucleophile and the electron deficient carbon atom, and then the partial bond that's being cleaved between the electron deficient carbon atom and the leaving group, which is the halogen. And so again, for an SN2 reaction, there's only 2 partial bonds, but for an E2 reaction, there's a total of 4 partial bonds. So you can see that there's a partial sigma bond that's being formed between the strong base hydroxide ion with the hydrogen atom. And then as this one is being formed, the sigma bond between the carbon atom and the hydrogen, so this is again the beta carbon right here, is being cleaved. And then at the same time, a double bond or a pi bond is being formed between the 2 adjacent carbon atoms. And while this one is being formed, the sigma bond between the alpha carbon and the bromine atom is being cleaved. So now you have a total of 4 partial bonds here in the transition state. And of course, another difference between an E2 and SN2 reaction is the product that's formed, right? So for an E2 reaction, what we get is an alkene, whereas in SN2 reaction, what we get is usually an alcohol, depending on the type of nucleophile that you use. So again, if you use a hydroxide ion, so in an SN2 reaction, you would get an alcohol. Here's a practice problem. Use curved arrows to show the movement of electrons in the following E2 mechanism, and then draw the structure of the transition state. So here we have an alkyl halide, a tertiary alkyl halide that's reacting with a strong base. And so this bromine atom is bonded directly to this alpha carbon atom. And so these 3 carbon atoms right here connected to the alpha will be the beta carbon atoms. And so let's just label those. So we have an alpha carbon here, 3 beta carbon atoms. And so these beta carbon atoms are all similar. They have 2 hydrogen atoms bonded to them. And so let's just pick this beta carbon atom right here. This beta carbon atom contains 2 hydrogen atoms. And so the strong base, which is this is an ethoxide ion, will attack one of these hydrogen atoms, and then the sigma bond will be cleaved between the beta carbon and the hydrogen atom, and then a double bond will form between this beta carbon atom and the alpha carbon atom. And then as this is being formed, the double bond here, the lone pair or the sigma bond right here between the alpha carbon and the bromine atom will be cleaved, and then it will be transferred to the lone pairs of electrons will be transferred to the leaving group, which is the bromine atom. And so that's basically the movement of electrons here. And so now it says draw the structure of the transition state. So what we have is this is the bromine atom, and then we have, let's see, we have, I'm just going to draw 1 hydrogen here. And then there's going to be a partial bond that will be formed between this hydrogen atom and the ethoxide ion, the base. And then this sigma bond will start to break partially. All right. And then a double bond will start to form over here. And then finally, the sigma bond will be partially broken. All right, so we have a total of 4 partial bonds here, 1, 2, 3, and 4. And then this oxygen right here will receive a partial negative charge. And then the leaving group will also receive a partial negative charge. So this is the structure of the transition state. So in order for E2 reactions to work, we need strong negatively charged bases like hydroxides and ethoxides. So remember tert butoxide that doesn't work for an SN2 reaction, it will work for E2 reactions because tert butoxide is a very strong base. It's a weak nucleophile because it's too bulky. And you can't really use that for SN2 reactions, but you can use it for E2 reactions because, again, it's considered a strong base. So the rate of the E2 reaction increases as the strength of the base increases. And so we have two examples of bases here that you can use. They're sterically hindered nitrogen bases called DBN and DBU. So they have a long name, and so they're abbreviated and shortened into DBN and DBU. So you can see that these nitrogens right here contain lone pairs of electrons, which makes them extremely basic, right? They're strongly basic. So here's an example of an E2 elimination reaction involving DBN as the strong base. So you can see here that the lone pair of electrons on the nitrogen will form a double bond first, and then this pi bond breaks, and then the lone pair of electrons then attacks this hydrogen right here in this molecule. Again, this is the beta carbon atom right here, and this is the alpha carbon. And so the sigma bond breaks and forms a double bond here. And then the sigma bond between the alpha carbon and the bromine atom breaks. And so what you now have is a new pi bond that's formed within this molecule. So this is one example of an E2 elimination reaction. The nature of the leaving group is also important when it comes to E2 elimination reaction. So the better the leaving group, the faster the E2 reaction rate is. And so when you look at these alkyl halides shown here, you can see that the trend in the leaving group ability increases from left to right, in which the iodine atom is the best leaving group and the fluorine atom is the worst leaving group. So when this iodine atom comes off, what we have is an iodide ion, and iodide ion is considered a weak base. And so you can always think of a good leaving group to be a weak base. So iodide ion is a weaker base compared to a bromide ion, chloride ion, or a fluoride ion. So in other words, the better the leaving group, the faster the E2 reaction rate is. And the type of solvent used can also affect the rate of E2 reactions. And so polar aprotic solvents increase the rate of E2 reactions. And so if you have solvents that are incapable of hydrogen bonding, then they won't be able to solvate the Bronsted-Lowry base too well, which allows the base to attack the hydrogen a little bit better. So again, that's the hydrogen that's bonded to a beta carbon atom. So one other difference between an SN2 and E2 reactions is the structure of the alkyl halide. And so depending on the structure of the alkyl halide, it will affect the SN2 or the E2 reaction. So if you remember, for SN2 reactions, this reaction prefers a methyl halide or a primary alkyl halide. And the reason why is because the nucleophile can attack the electron deficient carbon atom a little bit easier compared to a bulkier alkyl halide. However, for E2 reaction, it actually prefers a bulkier alkyl halide, like a tertiary alkyl halide. And the reason why is because when the double bond forms, that alkene or that double bond is stabilized by the R groups, right? These sp3 hybridized carbon atoms. So the increase in E2 reaction rate with increasing alkyl substituents can be rationalized in terms of the stability of the transition state. So if you remember, in the transition state, we have a partially formed double bond, and so we can stabilize this double bond by the presence of alkyl substituents, the R groups. And these R groups are sp3 hybridized carbon atoms that are able to donate electron density towards the double bond. And so that stabilizes the transition state, which means that it lowers the activation energy, which ultimately increases the rate of the reaction. So here we have two examples of elimination E2 reactions that basically illustrate the relationship between product stability and the rate of E2 reactions. So when we look at the first E2 reaction here, we have an alkyl halide reacting with a strong base, and this generates a mono-substituted alkene. And when we look at the second E2 reaction here, we have a tertiary alkyl halide, and this tertiary alkyl halide reacts with a strong base, and this generates a di-substituted alkene. And so because we know that a di-substituted alkene is more stable than a mono-substituted alkene, this tertiary alkyl halide will undergo E2 reaction at a much faster rate than the primary alkyl halide. So here's a table that summarizes the different characteristics of the E2 reaction. So an E2 reaction has second order kinetics and one-step mechanism. So that means that this is a concerted type of reaction similar to an SN2 reaction. The identity of R is a little bit different compared to an SN2 reaction. The more substituted halides react much faster compared to the less substituted halides. So that means that tertiary alkyl halides react faster compared to primary or methyl halides for E2 reaction. The E2 reaction is favored by strong bases. They're also favored by better leaving groups. So better leaving groups react much faster, and favored by polar aprotic solvents. So in this aspect right here, E2 is very similar to an SN2 reaction. So they're both favored by polar aprotic solvents and also by better leaving groups. So here's practice problem number 10. Rank the alkyl halides in each group in order of increasing reactivity in an E2 reaction. So the first step here would be to classify the alkyl halides. So for the first alkyl halide here, you can see that this carbon atom is a tertiary carbon, and so it makes this alkyl halide a tertiary alkyl halide. And the second one here, we have a primary alkyl halide. And the third one here is a secondary alkyl halide. So the tertiary alkyl halide here would be able to generate a more substituted alkene compared to the secondary or the primary. And so the tertiary alkyl halide would react the fastest, followed by the secondary, and finally the primary alkyl halide. And so in terms of increasing reactivity, again, the primary alkyl halide reacts the slowest, and the tertiary alkyl halide reacts the fastest. And for part B here, the first alkyl halide is a primary alkyl halide. The second one here is a tertiary alkyl halide. And the last one here is a secondary alkyl halide. So again, for this part right here, the tertiary alkyl halide reacts the fastest. So the primary is the slowest, followed by the secondary, and then finally the tertiary alkyl halide.